So today we are doing section 9-10 part B. We're starting with the warm-up. The first one, tell me a test that you use to determine convergence. Ratio test or the integral test, right? They both work just fine. It converges. I use the ratio test. Either one's fine.
Dude, the integral test took like no time.
Yeah, they're both fine. Okay, for the second one, this looks very similar to what series? 1 over n, right? So if you do a direct comparison though, does 1 over n converge or diverge? Diverge. This is less than 1 over n. Less than 1 over diverge is inconclusive, right? So you can't do a direct comparison, so you got to do a limit comparison, right? So if you do a limit comparison on this, what do you end up with? Diverge. Okay. All right, so the next one we have n factorial over 10 to the n. Two different tests you could use. Tell me one of them.
You could use a geometric series of two.
Just
No, wait, never mind.
comparative growth.
You could do a ratio test.
Ratio test. Does it converge or diverge?
Diverge. Yes.
There is an answer here. It's gone. It's gone. The answer is gone. Where did it go? Okay. Well, it okay, it diverges. I did the ratio test, but then someone in third period was like, "Why don't you just do the n-term test?" I'm like, "Oh, you're right. It's really fast with the n-term test, right?" Yeah. Okay. So anyway, so my ratio test answer is gone. That's okay. All right. Number 4. What's the easiest test to use? The root test. Yes. Or the root test. Yes. Okay. So if you do the root test, we get a limit. You take the limit of the root, the nth root, you end up with a half. If a half is less than 1, what does the root test say? Converges. This one converges. Okay, any of these, I worked out the first 2 right there. Remember guys, if you do the limit comparison test for number 2 and you get an answer that is positive and finite, that doesn't mean converge, it means they match, right? They match. So, okay. Good. Any other questions on the warm-up?
Can you go over the rule for the nth term test?
Yeah, the nth term test says that if the limit as n approaches infinity of the argument is not 0, it automatically diverges. And we know from comparative growth rates that factorials grow faster than exponentials, so this guy's going to infinity. Which is not 0.
I got it.
Good. Any other questions?
Learned in every way.
Okay, now for your homework from last night, I did one problem on the board. Was 17 the one you had a question on?
No, it was another one.
Oh, okay, I will put the other one on the board at the end of the lesson today. I'll add yours. Okay, was it one of those?
Yes.
Okay.
Both of those actually.
Both of those,
Those are the
okay.
3.
Okay, so 17, I guess the ones that gave people a hard time were the binomial ones, or not, I don't know. But anyway, 17 was a binomial one. So you have to get it in the form 1 plus x to the k, right? So you're looking at this somewhere, yeah, you're looking at this and you're like, well, gosh, I don't know how to get this in the form 1 plus x to the k, right? Well, we know the first thing that I dealt with is, I actually forgot to deal with this, and then someone in third period said, what about the 4? So then we had to go back. But anyway, so now the first thing that I dealt with was making this 4 become a 1. So the first thing I did was I pulled a 2, really a 4 out of, a root 4 out of the root, made it a 2 and put it out front. So then I end up with that, right? And now, so I have that 1/2 in front, 1 plus something to the k. So as long as it's 1 plus something to the k, you're okay. So your k is -1/2. I don't know if you guys remember, but we, on Friday, developed this big series with k's for binomial expansion, and you end up with 1 minus kx plus, and then it's well, it's plus kx, but the k is negative. So k times k minus 1 x squared over 2 factorial, k times k minus 1 times k minus 2 x cubed over 3 factorial, and you keep subtracting ones from k. Yes?
How come you, when you took out like a root 4, it was x over 2 the whole squared instead of x squared over 2?
Because I took out a,
Because isn't like the
it
coefficient...
would be x squared over 4, right?
Yeah.
So I just.
Oh, yes.
Yeah, so I just put it, you
I
could
got
keep
it.
it x squared over 4.
Yeah, yeah.
I don't know which way is easier and which way is harder. I put x over 2, so yeah. Okay, all right, so anyway, if you get this, so whenever you have these binomials, okay, whenever you have these binomials, so you get, I put the 2's to the bottom along with the factorials, and then you end up with this 1 times 3 times 5 times 7 times blah, 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 right? So when you have these, you end up with these funky little series within the series. The negative 1 to the n is fine, the x to the n is fine, the 2's become a 2 to the n, and then the n factorial is fine. The plus 1 has to be for that first term because it doesn't fit this guy in here. So you gotta put it on the outside. All right, so all of this, that's just 1 plus x to the negative 1/2. We want 1 plus x over 2 quantity squared, or x squared over 4, right, to the negative 1/2. So I just have to change my x to an x squared over 4 to the n. So I made this x to the 2n, and then the 4 to the n I threw to the bottom. And we're not done, but we're close. Then the fun part was, then I still had to distribute in that half that I pulled out at the very beginning. So I just multiplied everything by a half. So I put this half, the 2 on the bottom here. I made this 4 to the n times 2 to the n be 8 to the n, and then I have a half here. And then when I was all done, I checked the answer with what was online, and it was all exactly the same, except they wrote 2 times 8 to the n as 2 to the 3 plus 1, which actually is equivalent, so it was good. So there you go.
Of course.
I don't know what's on your test. I haven't seen your test.
Okay, you know what? You know,
I have no idea what's on your test.
Well, there'd be like one problem. But Miss Price, didn't you take our test?
I don't know what you're talking about. You have a test?
Miss Price, lying
Wait,
is not a good
No,
idea.
we don't have a test. Hey.
Okay, so today we're doing, I'm not gonna answer any questions about what's on the test or not on the test. So, tell the test.
For this. Can we put our pencils on the test?
Okay. What about the recording?
Never mind, Miss Price, never mind.
Okay, good. All right, so 910B. At the end of this lesson, you will be able to use operations to create a Maclaurin series for products and quotients of functions. We're not going to do quotients. We're just going to do products. So, honestly, I'll tell you this: quotients are not on your test, and they're not in your homework, and they're nowhere that I can find anywhere, and I don't want to deal with them right now, to be honest, right? So we have enough to do without adding quotients of Maclaurin series. So we're going to do products of Maclaurin series, and we're going to rock them, right? Okay. All right. Okay. We're also going to use power series to approximate an integral value with a specified accuracy. This is an important concept too, so make sure you take notes when we do this. But take notes for everything, right? The quotients, just whispering that to the world, right? Okay. Isn't that, I like that. I just came up with that. No, I was thinking about it. I like that. Okay. Find the first 4 non-zero terms of the Maclaurin series for g of x equals e to the x times cosine x by multiplying the appropriate power series. So here's the thing. Now I'm going to cover this up for a minute and just kind of walk you through. If you have to multiply just x times a series, you can multiply the series by an x, and it's fine, and it'll work. But if you have to multiply times a function of x times another function of x, that's where things get a little sticky. And you can't just take the two series and multiply them together, it doesn't work. So instead, what you have to do is write them both out in polynomial form and distribute all the terms, right? Yeah, so obviously we can't distribute all the terms. So instead, we're gonna just distribute 4 or 5 from each polynomial. So we'll end up with between 16 and 20 terms that we have to combine, because you have to combine like terms, right? Okay, when I first started doing this, I did not have a good roadmap. I found my own way. I developed my own method. I'm calling it the price method for multiplying series, okay? So, what I'm going to teach you today is my method. I think it works really slick. The method that I saw on the notes that I had for this section, I had a very hard time getting the problems correct. So here's how I had seen it done before. So, okay, not this, but this is just saying, hey, you can't just multiply the sigmas together. You have to actually write out the polynomials. You only need 4 terms for the answer, but sometimes you have to actually do more terms within the polynomials to get 4 final terms in the answer. So if you see us doing 5 or 6 terms, don't freak out. All right, so here's the 2 series written in polynomial form. So what we have is this times this, right? So remember when we used a FOIL? Okay, now here's the thing. So the notes that I saw, and by the way, you don't want to leave factorials because we have to find LCDs, right? So you're going to want to write them without any factorials. Okay, now the first time I saw these, the way that I saw them was the person took the 1 and multiplied everything in here by 1, not everything obviously, but like 4 or 5 terms, right? And then they took the x and multiplied everything by x. And then they took the x squared over 2 and multiplied everything by x squared over 2, right? And then they just kept going, and it was this giant list, right, of terms. And then they went through, found all the constants, added them together, found all the x terms, right, added them together, found all the x squareds, added them together, right? So I'm doing that, and I'm not getting quite the right answers. I'm getting some terms right and some terms wrong, and I can't figure out why my answers aren't working. So that was when I realized I wasn't going out far enough or including enough terms. And then I'm like, oh, well, how do we know how far we have to go? How do we know when we're going to include enough terms? And so then your book kind of did it a little different, but I couldn't quite follow exactly what the book was doing. So then I came up with my own way. So here's what I did. The first thing I do is I pick one of these and I just wrote it out up top. I picked this one. So when you're looking at this, right, I just picked this one and put it down here for no reason other than because I wrote that first, right? So I put that one there. You can put that one there, it doesn't matter. Now, in order to do this method, to do any of these methods, you're going to have to write clearly and cleanly and meticulously. So if you are a messy writer, these are probably going to be more difficult for you. Okay? Okay. So here's how you do it. So we have to multiply all of these by all of these, right? So I'm going to start by multiplying all of these by 1. So all I did, this is my first term here, so I'm multiplying all the terms in the first polynomial by the first term here, which is 1. Everyone okay with that? Okay. The next step then would be to go back and multiply all of them by negative x squared over 2. But when you multiply by negative x squared over 2, you line up your like terms. So your first term is negative x squared over 2 times 1. Line it up with your x squareds. Your next term is negative x cubed over 2. Line it up with the x cubes. Right? You want to line your like terms up vertically. And then, until you get a little bit ways out. Next thing we're gonna multiply by is x to the fourth over 24. So my first term would be x to the fourth over 24, I'm gonna line it up with my x to the fourths. Right? And then I multiply by x, and I get x to the fifth over 24, I line it up with my x to the fifths. You have to make sure you go far enough so that you include all the like terms for that degree of x. So I know my next term I multiply is negative x to the 6 over 720, right? The powers of x are getting bigger. So I know I'm not going to have any more constants. I'm not going to have any more x's because the next one would be an x to the 8th, right? The very first power would be x to the 8th. So the powers, there's going to be no more small ones, so I don't have to worry about missing any terms. But I have to make sure that I add enough across so that I include all of them. So for example, when I combine my terms, I combine all my constants, I get 1. I combine all my x's, I get x. To get my x squareds, x squared over 2 minus x squared over 2, they're gone. Boy, it's a good thing I went further out, because I have to have 4 terms, right? So now I have my x cubes. When you combine your x cubes, you need an LCD. So you have x cubed over 6 minus x cubed over 2, right? So this is kind of like minus 3x cubed over 6. So you get negative 2x cubed over 6 or negative x cubed over 3. When you do your x to the fourths, right, you add them all down, here's where I went wrong, was my x to the fifths. The first time I did it, I hadn't written an x to the fifth in my first polynomial, my first multiplication, and so I had these other x to the fifths, but I was missing a term that I wasn't including. That way, if you work vertically, you know there has to be a term for the lowest all the way up. All the way up. So if I were to add x to the fifth, I'd have to add all 4 x to the sixes. I'd have to add another x to the sixth term with each of these to make sure I include all my like terms. Right, does that make sense? Okay, so you only need 4. I gave you 5, but the question only said 4, and then you're done. You don't have to write it as a series. You just write it as a polynomial. So the correct answer for this one, that's actually the final answer right there, just those 4 terms. Because it just said for 4. So we need a minute to write before I move on. Okay, I will give you a minute to write. Do you have any questions while people are writing?
Why?
You know what's funny is if you need to come up with a series to approximate something, and we do know that using series approximation is used in real life, right? We have some standard series, and in order to create new series, it's easier if you can use existing series and use operations on them than try to develop a new series from scratch. So like one of the book examples was, hey, what if we wanted a series for tangent? You just do sine over cosine, right? So that kind of a thing. So for this one, it's, hey, what if we want a series for e to the x cosine x? We could just do e to the x times cosine x.
Because you have to do like a product rule. I was just saying, why not just like do it yourself?
No.
Is there a way to write this as a summation?
for x of that either.
I don't know, probably, I don't know.
Are we ever gonna have to do
I don't
right?
see the
You
pattern.
have to,
That would be a really
But
trouble,
like, you
tough
don't have
patterns to
that
figure out.
necessarily done
Right.
It's better to.
You're supposed to do more.
What?
Do you need another minute? You guys okay?
So how do you know that, like, so when multiplying by x to this, negative x to the 6 over 720,
Uh-huh.
how did you know beforehand to go all the way to, oh, do you just do 4 every time?
Oh, I just went out of the, you don't even need those.
Okay,
We
yeah.
didn't even need any of these. I just went out a little bit just to kind of show you. But we didn't actually even have to do that.
Okay.
I know, you'll see a pattern when you're doing these. It's kind of like, I know that since this polynomial goes by, the exponent of x goes by 2's, what's gonna happen then is I'm gonna go over 2 with each term that I add, right? It's like a step of 2 down. So if I only want the first 4 terms, technically I only have to go to here, except that one canceled out, so I had to go to here in order to get 4 terms. This guy was just extra for fun. Good, other questions? All right then, let's try one. So we are going to do e to the x over 1 plus x. Lucky for us, we already have a series for e to the x, and we have a series for 1 over 1 plus x, so we can multiply them together. Yay! So I want you to find the first 4 non-zero terms of the Maclaurin series for e to the x over 1 plus x.
So when will they give us the series?
We're going to talk about that, because that question's come up a lot today. It's going to come up even more in the next example. Yeah.
Does a constant count as a term? It's probably stupid.
Yes, a constant counts as a term.
Okay.
It's not a stupid question.
I think it was stupid for asking it. I saw Siri want you feel really stupid.
Funny called on Mark. Yeah.
Skip this one.
And then you've got to keep going because there's more.
That takes forever.
You get a common denominator. So like multiply, add multiply by 3. Because it would be, so it would be like negative 2x cubed or
Oh, okay.
how far are you
On the island, nothing.
Well, you need 4 correct terms in the polynomial. So you need to keep going until you don't have, like, here, when you step down,
So what was your final answer?
you're stepping by ones
1 minute.
with each time you multiply. So to get 4 terms, you should really just have to do 4 of these to get it, except that your x's drop out, so haha, you have to do 5 of them
She factors out the factorials, you do. It's like 2 factorials.
in order to get 4 correct
3
terms.
factorials,
Wait, isn't x to the third over 6 minus x to the third over 2, it's not like negative 2x to the third over
6.
6? Oh, I'm using the, I'm sorry.
That's okay.
I'm breaking it.
It's a lot of arithmetic. That's okay. It's a lot of arithmetic.
Whoa, how would you,
It's-
whoa.
There's a reason I failed like 4 grades.
I finally answered it there. A little awkward.
What's that, what was it?
So Arjun,
Oh, actually I got it. Never mind.
You sure?
We got it. You didn't have factorials, that's why. So,
yeah, don't leave factorials in because you have to find common denominators, so you're gonna have to write.
would you
times.
find like common denominators with the factorial though? Like, make it like
Yeah,
common
but
denominator
but
for
see,
factorial?
like 2 factorial times 3 factorial, how do you find an LCD? I mean,
You just multiply the top by 3 and then your common denominator would be
Okay.
3 factorial.
I don't see how that's really a faster and
Oh, okay.
simpler way. I would just use the numbers. Especially when you get to the 4th, you get some, you'd have a 2, I guess, you'd have a 2 factorial, a 3 factorial, and a 4 factorial, so you'd have to multiply the 3 factorial times a 4 over 4, and the 2 factorial times a 12.
Yeah.
But, I mean, it's the same as if you just had regular numbers, so.
Yeah.
Yeah, I see, either way. Okay. Good, other questions? Do you understand it?
Yeah.
It's time consuming, it's not difficult, it's just monotonous, right? Okay. Okay, last topic for chapter 9.
Oh, is that Eric?
Oh my god.
Old Dunbar.
Oh, you wanna see a flash one? Yeah. Yep, woo! Okay, alright.
Were you taking a quiz yet? Are you gonna take your quiz?
Yeah, I was. I'm like, oh, there needs to be an effect. Okay, so, alright, last topic, how to use power series to approximate an integral with a specified error. We're gonna use power series to approximate the integral of arctan x over x with an error less than 0.0001.
Yay.
Yay! So, the first thing we need is we need a series to represent arctan x over x. Then we're going to integrate it,
That's no
and then we're
problem.
going to use our error methods for finding our approximation.
Just skip this problem.
So,
I don't think this is on the test.
It's probably not gonna be on the test.
I don't think this is on the test.
I checked
So,
it.
I haven't seen the test. I don't know. You can make guesses all you want of what's on there and what's not, but I have no
But I
idea.
checked with the college board.
Okay, yes, check with the college board on Mr. Thomas's chapter 9 test.
It worked.
That's what I was.
Good. I know.
Sassy.
Okay, so anyway, the series for arctan x, this is it in polynomial form and this is it in series form. I find these problems a lot easier to do with the series than with the polynomials, but I'm putting both just in case you want to use. You can use either method, right? There's no rule. Yes.
For something like this, can't you just divide that series by x?
Yes, you can.
Wait, are we doing that?
Yes, we're
Oh,
going to.
okay. I
Yes.
thought we were gonna do like the multiplication thing, and I was freaking out when I was trying to.
No.
that series?
That's the question of the day. All right, should I answer that now or later?
No.
Later.
Please.
Why later?
Okay,
Give
so,
it to us.
here's how the test is organized, and it's not like there's just one of
I
these,
think I haven't
but,
seen it.
oh, I haven't seen the test.
This
So
is
I'm
how you
guessing,
have it.
this is my
okay,
guess as to how the test is organized, right?
We not
Okay, all right, if I were to make a test, here's what I would do, right?
Is that what you do?
I would
Give us
maybe
something for
start with some sort of a function, right, where you have to create an initial series. So, do you guys remember way back in 9-9, when, one section ago, when we gave you like an a over 1 minus r, right? And so, here's the sum of geometric series, take that sum, right, get it into a over 1 minus r form, and then write the power series for it. Okay, that ring a bell, right?
No.
Okay, okay.
Not a loud one.
Or the other type would be like a Taylor, right? Find the Taylor polynomial for blah blah blah, then write it as a series, right? So there's a couple ways we can start you from scratch and make you create a series, right? Okay, so say we have something from scratch, and let's just say it's something simple, right? Let's just do sine x, right? So you've got your polynomial, you've got your series for sine x, and now say we ask you for like, sine x squared, right? So you're just replacing whatever, right? And then you have to integrate it, right? Right, it just builds on what you've done. So it's not like there's any series where you have to have memorized that grid, because everything that you create, you will create and they will build, right? Now find the integral of sine of x squared from 0 to 1 with, an accuracy of this, right? It's all stuff that you created and built on.
So if you screw up
But
first.
if you get the first part wrong, so here's the thing. Okay, so as Amanda said, there's no double jeopardy unless you make it like completely change the scope of the problem, right? Where everyone else is doing the integral from 0 to 1/2 of arc tan x over x, and you're doing the integral from 0 to 1 of x, right? Something like that. You can't just change the whole problem
Wait, you can't?
and make up your own that's like 10 times easier, and then I give you full credit for it, right? So, but say you do the whole thing, like, remember the binomial one that I just did, where you had to pull out a 4 and say you pulled out a 2 instead of a 4, like something like that, right, where you had a 2 instead of a 4, just some little constant change. So it's say like you have a 2 where the rest of us have a 4. That's fine. I mean, obviously you'll like lose a point or two for having the 2 instead of the 4, but here's what I'm asking for you, because then you'll just be working with the wrong thing the whole way through. I will grade it as though, using that the whole way through. I'm asking you not to do that, because then I have to find the error and plug it all with your function into my calculator to see which term falls less than 0.0001, and then find the sum with your function from whatever to whatever, and I really don't want to do that 90 times, right?
So you're not going to?
So,
Why would you theoretically
So
make
can you
a
just
test
give us
that
all full
built like
credit for
this,
these
then?
types of problems if we show effort?
it's a good question.
Plus with
So,
the first problem.
yeah. So anyway, so my humble plea is please just don't do that. Okay, so get them all right and then life will be good. So, yep. All right. So anyway, so here we go. We start with arc tan x, right?
Are you done?
Which, by the way, you guys built last week when we did 1 over 1 plus x, and then did 1 over 1 plus x squared, and then the integral of 1 over 1 plus x squared. And look at that, there's arc tan x. Oh, right? Yeah.
You made it to a geometric
Yeah.
square.
Okay. So anyway,
We are there.
so arc tan x over x is literally just dividing out an x from every term.
Try
For your theoretically made test, do we have to memorize the arc tan x, or will that be given, will those type of things be given to us?
You don't have to have anything memorized. You will be building everything.
That does not help.
You want to
So we don't have to memorize it.
It's way easier to memorize.
Yup, memorizing is easy.
So say
Just
like, we get you to build 1/x and then you have to do log x, right?
Yeah.
Everything can be built.
Okay.
You will be building. Everything can be built, yes.
Let's say we had memorized like arctangent over x, or like arctangent x, do we have to kind of go through the whole process, or could we just do
It's
that?
not that much of a process, really.
But
And you'll be doing the process the test is multiple questions, so you will have to do it anyway, the questions. There's not that many, it's not like it's 14 problems that, like, one to the next, it's usually just a couple, right? Okay, alright, so anyway, so hopefully you guys, if you're given arctan x, you can divide out an x, right? Okay, everyone okay with that? Okay. So now what we're doing here is we're setting up, so that's arctan x over x. So we need the integral from 0 to a half of arctan x over x. Well, we need to integrate. So if you integrate with the polynomial, right, you're just integrating literally each term. Or you can integrate with a series. Remember, you just add 1 to the power of x divided by power.
Yeah.
I like the series, I like working with the series. But I know from Ms. Thomas there is definite benefit with being able to work with the polynomial when you're doing derivatives and integrals. But I am so far, without having done too many BC AP exams, I'm a series person. So what we end up with is this series that we have to evaluate from 0 to a half. All of your lower limits for your integrals tonight. Okay, all right, so you plug in a half, and you can either plug into the polynomial, right, or you can plug into the sigma, because when you plug in the 0, it's all 0, right? So I like to plug into the sigma, and the reason I like to plug into the sigma is because then you get this lovely thing that you can plug into y1 and find, what kind of a series is this?
Alternating.
Alternating. If you guys remember, we learned two types of error, right? We learned alternating series error, and we learned the Lagrange error formula, right? Alternating series error is the one that you guys like better, because then all you have to do is find which term falls below your error threshold, and then add all the preceding terms. Do you guys want to take a second and try this one? Take a second, put this in y1, see if you can figure out which term falls below. It's 0.0001, 3 zeros and a 1.
Is it just me, or are like a ton of the integrals have like 1/2 as a common theme?
Plug it in.
I honestly don't know.
I'm just noticing that in my homework and stuff. I'm not complaining.
When the Star Trek series first came about, they weren't quite sure how they wanted Leonard Nimoy's character to behave. And it was when he used the word fascinating that they decided that that summed up the character best. And they went from that word forward and developed this character.
Great leap forward.
What's part of that?
I was fascinating. Did you not, were you not quoting Spock?
Oh, of course.
Did you know that the automatic doors that everybody thinks makes them a Jedi was originated from Star Trek?
Oh, but I gotta do
The automatic
Like
doors.
the ones that like slide open, like at like a Target you walk in and the doors open up, that was from Star Trek.
No way,
Yeah,
really?
Yeah, cause you know like when they're on the like the control deck or whatever, like when people come in
Oh,
the
sure.
doors slide open.
Yeah.
Apparently then they just had people standing behind you like open
Of
it up and
course.
close it.
Yeah.
And then people were like, oh, that's a good idea, and then they invented it. Same thing with flip phones. Flip phones were also Star
Oh, from the communicators?
Yeah.
Yeah, very cool.
Star Trek attributed to society.
I'm giving
Yes.
Which
Which term did you find fell below .0001?
Ace of 4.
Ace
Try to find the
of
numbers or
4?
like.
That is also what I got.
Trying to find the character.
Yes, ace of 4. So, do we include ace of 4 in our sum?
No.
No, you sum from n equals 0 to 3. It's the first 4 terms, but it's from 0 to 3.
Did I put
This
that
is the
in?
thing
I
with
know
the
I did
8
not,
digits,
I'm an
right?
idiot.
I plugged
This
my-
is where you're gonna have to put 8 digits. I don't have 8 digits on this example, but you will on your test have to put 8 digits.
I figured that.
I think it, what, are you confused? I plugged that in and I got n
Yeah, I
equals
didn't
4.
see
Oh.
it, so.
You got n equals 4? Oh, yeah, that's right.
No, like go to a sub 3.
Yeah,
Right.
that's what we have.
Never mind, it goes to the I saw the 5th term and I was thinking.
Yeah, the 5th term is a sub 4, because you start with 0.
Oh.